This video tutorial will be a demonstration of the usage of simple gain transfer on an actual measured dipole and the viewing modules used to view the results. We'll first load up the data file named dipole.dat, which is located in your advanced directory. Now, recall the measurement from reg1, which sets this data as your currently active data. Your currently active data may also be referred to as reg0. After loading, we can see that the measurement was taken from 2 GHz to 3 GHz and contains nearly 36,000 points of data. We can see the as-L extent details by clicking this button here. This shows us that the azimuth measurement extents were taken from 0 to 360 degrees and in 10-degree increments. It also shows us that the elevation measurement extents were from 90 degrees to negative 90 degrees, also in 10-degree increments. Now, in order to determine the gain transfer amounts, the first thing we need to do is calculate our path loss. In this case, our measurement distance was taken at 1 meter, which is the default. Since we don't have to change anything, we simply select Continue. If you've already determined your path loss calculations, the path loss button will be green, and it will also present a warning when you click Continue. Now that the path loss has been accounted for, we import the appropriate reference antenna. In this example, our measurements were taken using our reference horn antenna. Click the Example Data for this horn button. This will load the necessary reference horn data and automatically display the data in Notepad. Close Notepad and then click Continue. Now we're ready to invoke the gain transfer module. This module offers standard linear gain, circular gain, and total power factor. In the list of requirements, it explains what things we need to have set before we can calculate gain. In this particular case, we want to select linear gain. Upon clicking, we get a notification that the power gain data has been saved to reg0, which is your active data, and reg4. Click OK, which closes this window and brings us back to the main screen. Here you can see that in reg4 it has saved and titled the data as AUT linear gain. From here we can begin to examine our data. The best place to go first is the polar plot. Select the polar plot button and select a low dB division setting. Next, click the Go to Max Signal button, which shows us that the maximum amount of power gain is 4.94 dB at 2.16 GHz. If we click the Over Frequency Plot button, it will display a frequency graph of the gain data at the current as-L location. We now make changes to the azimuth slider. We invoke elevation contours in the upper right. If we invoke changes to the elevation slider, we invoke azimuth contours. There is also an option to view full elevation cuts in order to view the backside of your antenna, which does not actually get measured. Now we exit out of this window by clicking Exit. Next, we're going to examine the spherical data by clicking the spherical 3D as-L button. In this window, the first thing we're going to do is click Set from Polar Plot, which sets the frequency to be the same as in the slider in the Polar Plot module. Now we're going to keep the default 20 log setting, but set the as and L views to 45 degrees each. Now we'll plot with these settings by clicking the Generate Plot button. This will produce a full 3D representation of the dipole gain, which enables you to view it from any angle. This horizontal dipole was actually measured L over as opposed to a traditional vertical dipole. We can see that the process gain data was as low as -40 and as high as 5. The peak value is shown over here, where one is also able to add an isosphere. You might want to add an isosphere to enable a measurement grid. In this example, we're going to add a 1.9 dB isosphere with a 5-degree grid resolution and replot the data. By invoking the viewing rotator, we can see the areas along the measurement which are 3 dB down. We're going to exit the spherical mode and invoke the 3D as-L frequency plot. In this window, you'll see there are 3 options: elevation versus frequency, azimuth versus frequency, or azimuth versus elevation. If we select the as-L option, the slider changes to frequency and we can move it to our desired frequency. We can use the dB plot option and create a visual representation of as-L for the current frequency slider location. If we wish to see contours, we simply select that option. In this case, they're set to -3, -6, and -10, but can be changed to any desired values. Now we click the Plot as L button, and here we see the contours with the corresponding gain values. This is most useful for beam measuring. If we add an isoplane, we will have a grid we can then view the contours against. If you wish to make a color plot, or specifically an azimuth color plot, we would adjust both of the as-L viewpoints to 0 and replot. Now we can examine our basic color plot. The other option is the 3-point gain module, and this enables one to determine the solution to the Friss equation using 3 separate antennas by comparing each antenna to one another. For example, A to B, B to C, C to A, etc. This enables a direct solution for the Friss equation. The path is still required. While this works great in some situations, it doesn't work for every antenna. The gain substitution enables a known standard to be measured in the entire length. Then an AUT is inserted and remeasured. The reference technique eliminates the path as a necessary known. There are some options such as scaling Reg3 to a known constant, which would be that of your own reference antenna, or compare the antenna under test at the peak only, and finally, compare the antenna under test at every reference point in azimuth. Those are the 3 basic options for gain determination.